Okie dokie. So we're on to section 5-2, which is verifying trig identities. So our big essential question now is how can I verify trigonometric identities? So verify means to show that it's true or to prove. So what we're starting to march forward towards is that idea of equation and solving trigonometric equations. In other words, equations that have trig functions in them. So if we can verify and show that sides are equal, that's kind of one step closer to that. So we're going to be utilizing all of the strategies we talked about in the simplifying section, but some people find this even, I guess, a little easier. One, because we've already been practicing it, but also because you have something on the other side. You sort of know what you're shooting for. Sometimes when we're simplifying, it's hard to know when we're done. You know, you're always asking yourself, is there any other substitution I can make? Is there any other order of operation I can do? In this case, you know when you get the sides being equal to one another. So let's take a look at sort of the overarching kind of keys to doing this. So it's really being able to use the fundamental identities and algebra to rewrite the trig expression. So we're going back to that list that we did in section 1 of the reciprocal, the Pythagorean, like all the different things we can do to substitute to be able to rewrite and transform one side into the other. So again, getting ready for that equation solving. So there's lots of different strategies again that we use to do that. So kind of pause as you need to as we walk through them. But remember what identities are first. An equation, so an identity, it's an equation. There's an equal sign. That's true for all values in the domain. That means for whatever angle we're talking about in our trigonometric function, whatever the domain might be. So like for sine and cosine, all real numbers. This equation, this statement is true for every single one. It doesn't matter what angle you pick, positive, negative, decimal, whole number, whatever it is. For every single angle measurement, this statement is going to be true because it's a trigonometric identity. So it's an identity using trig functions. All right, so a conditional equation, then, what we're going to be talking about if we're talking about a conditional, is only true, it's like what we're headed for, is only true for some values of the domain. So like solving for a particular equation. So a conditional means it's only true for certain values, not all values. So this is only true for some of the values of the domain, which is what we're doing when we're solving things like 3x plus 5 equals 15. We can solve this equation and we can get an answer, and it's only going to be one value of x, right? It's not going to be an infinite number. It's not all values. This isn't a true statement for any value of x. It's only a true statement on the condition where the x is the value it needs to be to make 15. So that's why they call those conditionals. So ultimately, we're going to head for conditionals. We're going to be looking at ones that only have certain values. But for today and the next couple of days, we're going to be talking about identities, ones that are true for all values. All right, so we're going to go through this list of guidelines. So we want to make sure that we have our strategies in place. So one thing is you really can't assume that the two sides are equal. So it's over in the little bubble over there. So I think a lot of times people are like, oh, I'm verifying it must be true. Well, in real life settings, we can't necessarily assume that. So what we try to do is only work with each side. So what this means is you can't take something from one side of the equation and move it to the other like you would normally do when you're solving an equation, like a conditional sentence. We can't assume that they're equal. We're trying to show that they're equal. We're trying to verify that. So you really have to work with the two sides separately. We can't move things from one to the other. So no operations from one side to the other when we're verifying. But here are some things that we can do. We can work with one side, the more complicated one usually, right? So if one side's like 7, there's not much to do over there, right? We're going to work with the more complicated side, trying to make it match the other one. Another thing, look for some basic algebra things to do. Things like factoring, order of operations. Are there things I can do? Multiply, subtract, whatever it is. And getting a common denominator. Quite honestly, if we have fractions, a lot of times, because these are trig identities, we have a lot of fractions, we can look for getting a common denominator. Use identities for substitution then. We're going to make substitutions, right? We're going to substitute in different things to try to get them together to do all the things we did when we simplified. Convert everything into sine and cosine. So sometimes if we're looking for substitution, the easiest way to do that is just change everything into sine and cosine and see what happens. See if we can make something work. And again, I'm going to add off to the side here, write an algebraic expression. So writing it as an algebra sentence. So sometimes just saying like x instead of cosine of x just helps you visualize what you might need to do. And I think the most important of all, like the absolute most important of all in simplifying or verifying, do something. try something. I mean, doing nothing really is going to get you nowhere. So this is one of these things where we have to have a little grit and perseverance. Sometimes we try some and it bombs. That's real life, folks, right? That happens all the time. So we just have to try something and see what happens. If it doesn't, it's not very fruitful, it doesn't work really well, then we'll try something else. But we have to try something. So we have things that we can do that we can try to make it better. All right, so we are going to try something here. So we're going to go through a few examples here for day one and just see if we can start using some of those to verify this identity. So we have sine of theta, tangent of theta, plus cosine of theta equals secant of theta. So here's our first one we're going to take a look at. Notice the equality. So there's the difference. This is an identity. We're saying that this is supposed to be true for all values. They're telling us to verify the identity. So I'm going to work with one side or the other and see if I can transform it to make the other side. So I think I'm going to be looking over here on this side because that's the more complicated side. Secant of theta, not a lot to do with that. So we're going to try to see if we can use some of those strategies. So let's take a look on the left. And for a lot of these, what I think would be really super helpful is if you kind of try something on your own and then watch what I do. And again, there's different ways to do these. So I might not be presenting the only way that works. Remember, there's lots of different options. But sometimes you taking that moment to ask yourself, okay, what functions do I see? What operations do I see? So looking for that over here, because then that gives us a little bit of an idea about what we want to do first. Because remember, we can substitute, we can do order of operations. We can think of it as writing it as an algebra thing, all sorts of different options. Right now, though, I see three different functions, a sine, a tangent, and a cosine, which right now it's kind of a mess because none of them can be put together. I think substitution is going to be the way we want to start here. So I'm going to rewrite everything, and I'm going to even go to the strategy of rewriting everything into sine and cosine. Since I already have a sine and a cosine function in here, I think that might be a good plan. So tangent's the only one that's kind of missing out. So I'm going to go ahead and think about what tangent would be. If you use your pink sheet or that list in 5.1 in your notes, tangent is sine over cosine of theta. So I'm going to rewrite it like that and see if that helps us at all. Now, it's kind of a pain, but I think it's a good idea. Notice how I wrote sine over 1 and cosine over 1. Anything, if you have a fraction in your statement, write everything as fractions, because then when we do order of operations, we'll be less likely to kind of hose that up later on. All right, so let's take a look at the left-hand side here. So I see a multiplication and I see an addition. I need to multiply first. So top, bottom, bottom. So that would give us sine squared over cosine of theta, and then plus cosine of theta over 1. And on the other side, we're still shooting for this secant. I'm not really going to worry about that side. I'm going to try to make it that side. That's what I'm shooting for, which is why, again, some people think this is a little easier. Okay, so still on the left, I need to add. When you're adding two fractions, remember you need a common denominator. So right now it is not common. So I'm going to multiply top and bottom by cosine of theta for that second fraction to get a common denominator. So sine squared over cosine of theta plus cosine squared of theta over cosine of theta. Oops, so some people are going to be able to sort of do this in fewer steps. I caution you to try not to do too much in once because it's hard to follow logic. Another thing that's really helpful to do sometimes, people start doing things like this, like numbering your steps, so we can really see what's happening. So I'll try to use that habit here a little bit as well, if this is easier for you to follow the work. So let's put those common denominator terms together. So they are not like terms, but I can definitely combine them into a single fraction over my common denominator. And remember, when you do put things together as a common denominator, like 1/7 plus 2/7 gives you 3/7, right? So it'd be over cosine. So just to use your arithmetic skills that you know. Now this looks like we've kind of gotten to a sticking point, but I want to draw your attention to this numerator again. So remember how we substitute, we do order of operations, then we ask ourselves, is there anything else we can do? I think there's a substitution we can make. Take a look at your pink sheet, see if you can find anything. When you see squares, you should be thinking about which of those identities. Greek guy, Pythagoras. So Pythagorean identity, what's sine squared plus cosine squared? It's 1. Another great thing to look at is look at the other side of the equation. You want secant. Wouldn't that be nice if it was 1 over cosine? Because guess what? What's 1 over cosine? Now we again can make that substitution. Final step 6 here. Secant of theta is equal to secant of theta. Your last statement needs to be identity. Same thing on each side. So we have verified. We've checked it. We know that this is true. This is a true statement for all values. It doesn't matter what angle you pick, they will be the same on both sides. So that's our kind of our strategy, how we go forward. All right, let's take it. We're going to do a bunch more. The best way to get better at these is by doing them. It's this definitely experience makes better on all of this. So being able to recognize things as you see them. All right, so go ahead and get this one jotted down. We'll take a look and see if we can verify this identity. This is clearly one where there's one side is way more complicated than the other. Pretty sure we could handle the equals one side. It's the junk on the left we have to deal with. So first order of business, everything's squared. So I'm wondering if there's some things that we can do to do some simplifying. So this numerator, sine squared plus cosine squared, we just talked about this. I think there's a substitution. I'm going to kind of justify my steps here. So I think we're going to try to do some substitution. What is that numerator then? Sine squared plus cosine squared is just 1. The denominator, cosine squared and secant squared, those are two functions that have a very special relationship. Those are reciprocals, right? So I'm going to make a substitution down in the denominator as well. Secant squared would be 1 over cosine squared. And let's just be careful that we're okay with that, because remember, cosine of theta is 1 over secant, or secant is 1 over cosine. You can say it either way, they're reciprocals. So that means that cosine squared would be 1 over secant squared, or secant squared would be 1 over cosine squared. That is true. So I can write secant squared as 1 over cosine squared. Now watch what happens. I can do order of operations. So I'm going to do order of operations here with my fraction. So let's see what happens. In the denominator, the cosine squareds divide out, and we're left with 1 over 1, which is most definitely 1. We've verified that identity. So this idea of looking for things to try to make the functions the same. So I substituted, I did order of operations, and I was able to verify pretty quickly. All right, let's try a couple of the ones that they gave you in your note-taking guide. So let's take a look at example 2. They're trying to have you prove this identity where you have quite a few terms going on here, but there's some work I think we can do to simplify. So I'm going to go ahead and copy this over here while you think about what things do you think you could do? What kind of options would you have to be able to work with one side or the other? So if I look at the left, I'm looking at this and thinking, gosh, what do I normally think when I have two binomials next to each other that are multiplied? Well, I'm normally thinking FOIL and try to put that together. So I think kind of starting with our strategy of like do order of operations first, that might be a good thing to do. So I think I'm going to do some order of operations here and just do some of that and see if I can just get less terms overall right off the get-go. So I'll leave the sine squared for the moment. Let's do the order of operations here in FOIL. So first would be cosecant squared. Outsides and insides, this is difference of squares. They're going to add to 0. So all you're going to have left is -1. Fabulous. That made that so much easier already. And we're shooting for 1 minus sine squared on the other side. All right, so first thing we did is we did some order of operations. We multiplied that together. Let's think about what else we could do here. Keep going with order of operations, I guess. We could do that first, or we could substitute first. I think I might do some more order of operations here and just see what I get. So I'd have sine squared of x times cosecant squared of x, and then minus sine squared of x. I'm also using the other side as a guide here. I want a negative sine squared of x and a 1. Well, I already see that negative sine squared of x. Gosh, it would sure be nice then if this were the 1. And take a look. Think about it. Aren't cosecant and sine reciprocals? So I'm going to make a substitution here. I'm going to replace cosecant squared of x with 1 over sine squared of x. Remember, if it's a fraction like that, we can also raise them to powers. So because 1 over sine is cosecant, 1 over sine squared is cosecant squared. All right, so let's see what happens then. Our sine squareds divide to 1, and we're left with 1, step 4 here. 1 minus sine squared of x is most definitely equal to 1 minus sine squared of x. So we have verified, we showed that it's true. Now, again, there's many deviations that we could do in this. Some people maybe would have substituted right here and put in the 1 over sine squared and then distributed. It would have been exactly the same thing, just a little bit different order of operations. A lot of it just depends on what you see first and what's easiest for you to deal with. What are you comfortable with algebraically? But again, remember our goal is to try to make one side the same as the other. Let's try a few more. These are really great ones to talk about. All right, we got the Greek letter alpha going on here. Choose your letter for your angle. That's an alpha, which is great. It works fine. And we see a really high power. So we see a fifth power, which is kind of crazy because if you look on your pink sheet, there's nothing at all there that has a power of 5. So we're not really going to be able to do anything with the left-hand side there because we don't have any power of 5 substitutions. However, we can probably do things then on the right-hand side here. So let's see if we can take a look and if there's some things that would work. So let's kind of analyze over here. And again, take a peek at it. Pause the video so you can think about it first. So I see a cotangent, a cosecant, and a cotangent. So 2 of the 3 functions are the same. They're raised to different powers. There's nothing on your pink sheet that's a cotangent cube though. So when I see higher powers, one of the things I'm going to be thinking about as a strategy here is factoring. And then I'm also going to rewrite this one as an algebra thing. So I'm going to rewrite as algebra, an algebraic expression, because I think that might help you see what we need to do. So over here, this is kind of like saying, let's use x for cotangent. So it'd be like x cubed. Let's use y for cosecant, y squared minus x cubed. Couldn't you pull an x cubed out of that? So factor, and what would that leave you with inside? It would be a y squared minus 1. I think that's the strategy we want to go with here so we can simplify that. We don't have really the other substitutions to make because there's nothing on there for cubes either. So let's pull out that cotangent cubed of alpha. What that's going to leave is cosecant squared of alpha minus 1. So we have that kind of algebraic idea. Now it doesn't seem like, oh gosh, seems like it's more stuff. However, let's take a peek at your pink sheet or at your identities list from 5-1. Take a look inside there. What is cosecant squared minus 1? Well, that's cotangent squared. So I can make that substitution. So now I'm going to substitute on this next step. I'm going to try to make this easier. That's a cotangent squared of alpha. All right, so step number 1, we did some factoring. Step number 2, we're doing a substitution. And watch what happens then. What's cotangent squared times cotangent cubed? Most definitely cotangent to the 5th. And you verify the identity. So it's you being able to understand what the different strategies are. I don't have anything I can substitute, so let's try some algebra and some order of operations, see if I can put some things together. All right, I'm going to add a couple of my own here to finish off this day 1 so we can talk a little bit more about verifying. So we're going to do just a couple more just to make sure we've looked at all the different strategies that you would need to do. So we're going to try to verify this one. 2 cosecant squared of new Greek letter. Any guesses? Second Greek letter, beta. So we just did alpha, so now we're going to do beta. So you can use any Greek letter for these. So what we're going to take a look at is, gosh, how can we verify or show that this one's true? So let's talk about our options. Probably want to work with the right-hand side. More complicated, there's actually an operation we can do of addition. So we're supposed to add 2 fractions together. So in terms of substituting, like it's already just in cosine, which is one of our easier functions. 1 minus cosine, 1 plus cosine aren't anything by themselves. They're not squared. They're not Pythagorean. I think our only option here is to just do order of operations. We really can't do anything else. So our task in front of us is to add 2 fractions together. So what do we need? Common denominator. So we're going to multiply the first fraction by 1 plus cosine of beta, top and bottom. So remember, when you get a common denominator, you're multiplying the top and the bottom. Then 1 minus cosine of beta, top and bottom for the other side. So our first step here is we're going to get common denominator. So let's see what that looks like. So we'd have 1 plus cosine of beta. Now in my denominator, I'm going to go ahead and multiply those together. So when I multiply those together, 1 minus and 1 plus would give me 1 minus cosine squared. So I'm just going to go ahead and simplify that right now, just so it's a little bit easier to write. For this one, I'd have 1 minus cosine of beta over the exact same denominator. You could leave it as 2 separate as well. It doesn't really matter, whatever you think is going to be easier for writing down and moving forward. All right, so now we have a common denominator. We're still trying to add. Don't forget to actually add them now. So we got the common denominator. Let's put together like terms. So it looks like the 1 plus 1 would give me a 2. Look what happens to the cosines, though. Add to 0. Great. So we made it a little bit easier already. So what I just did was some order of operations. I actually did the addition. And let's see if we can get to verifying this. So let's take a look at the denominator now. So we must have to do some substitution because I don't have the same functions on each side of the equation. So let's see if we can substitute. So let's look at the denominator. 1 minus cosine squared is Look at your Pythagorean identities, sine squared of beta. So I think that gets us into a really good position here because we can make another substitution here. What is sine squared? Well, remember sine has that relationship with cosecant, they're reciprocals. So when you think of what is sine of beta, it's 1 over cosecant. So I can make that substitution that this is 1 over cosecant squared, because remember this is sine squared. And then I can just simplify that expression and we're going to have the other side. So make that substitution and then think about what you're doing here. We're going to multiply by the reciprocal. So 2 is like having 2 over 1 times the reciprocal of the bottom. So cosecant squared of beta over 1. So we're doing our order of operations here. And again, a lot of people will do this in fewer steps, I guess, but I'm just trying to show you all the work so you can follow what we're doing. So 2 cosecant squared of beta would be equal to 2 cosecant squared of beta. So we've proven, we've verified that identity. So again, trying to know what you're shooting for on the other side and using this combination of order of operations, substituting, and seeing if we can make them the same. All right, let's take a look at our last one. We're going to verify this identity. So I'm going to have you again, if you could, pause the video, write it down. Think about strategies. What would be the easiest thing to do first? And we'll talk about what options are in front of us. So when I look at this, again, I see two binomials. I know they're not the same function, but gosh, when I see two binomials, I want to multiply them together because that's doing order of operations. And we can probably agree that this left-hand side is more complicated than the right, so I'd probably work with the left. So I think my first step would be, let's just do FOIL. Let's do order of operations and see what that gives us. So we get secant squared of x times sine squared of x, and then minus secant squared of x. That's first outsides. Insides, minus sine squared of x, and then plus 1. Be careful in the sign for that last one. It would be plus 1. And what we're shooting for is that should be equal to negative sine squared of x. All right, let's take a look at the left-hand side. Now we just have all sorts of different functions. So here's where it might be appropriate to do some substituting. So we started in step 1 with some order of operations. Now I would do some substitution to try to make things the same. So I see secants. Gosh, let's change those over into 1 over cosines or cosine squareds, as this case would be, and see if we can try to make some functions that are a little bit more alike. I'll keep the signs as is for right now and see if we can get some things to go together. Alrighty. So let's do some order of operations. I see a multiply, a subtract, and an add. So order of operations, we'd multiply first. So we're still doing order of operations. We get sine squared over cosine squared minus 1 over cosine squared minus sine squared plus 1. So this is a little messier in terms of what we have left, but let's see if we can get some things going on here. So we have subtract, and an add. Okay, well, we have the two fractions, and we can subtract those because they have like denominators. So we have a sine squared minus 1 over a cosine squared. And then we have our minus sine squared plus 1 equals minus sine squared of x. So if I look on the left-hand side, I must be able to put a few more things together because I really just want to end up with this, right, equal to that. So I think I need to work some more with that fraction. So I have two different functions right now. I have a sine and a cosine. Let's change over the sine squared so I can get it the same as the cosine squared. So we can make that substitution. So I'm going to substitute again. What's sine squared equal to? Well, it's 1 minus cosine squared. So I'll recopy everything else that I have here. And I think what you're going to see then, hopefully you're seeing it already, is I can do some more with that fraction. The ones, 1 minus sine squared of x. So we would have, looks like the ones would add to 0. And so I'd be left with negative cosine squared over positive cosine squared. And I think that's going to help a bunch because I think I can simplify that some more. And again, I know a lot of you are going to be able to probably see a lot of this and do a lot more in one step, but I just want to make sure everybody's seeing what's happening. That's like saying x squared over x squared. So we can divide those terms out. It would leave a factor of negative 1 though, right? Because it was minus cosine squared, but that's exactly what we need it to be because we're going to still continue to do some order of operations here. What happens with the ones? Well, they add to 0, and you're left with negative sine squared of x equals negative sine squared of x. So we verified that identity. Again, you could have taken lots of different routes in this. Some people maybe would have substituted first and then multiplied. Ultimately, you're going to end up in the same position. Some people maybe would have left this 1 over cosine squared, just to show you a different option as the secant squared, and then they would have written sine squared over cosine squared as tangent squared, and then they would have done tangent squared minus secant squared, and put in the identity for that. You could do that too, so you got just lots of different options. So I just chose to do it with sine and cosine, so it worked really well. So remember our ultimate goal. We're trying to show that one side equals the other. Lots of different ways to do that, but we always go back to our strategies. Order of operations, substitution, writing things as an algebra statement, looking for factoring if that's appropriate. And remember, we always just want to try something.